Okay, today we're going to have a look at the logistics equation. Now the logistics equation is equations in the form y dash is equal to e to the y. Very similar to our first order differential separable equations in the fact that it's y dash equaling something. The only difference with the logistics equation is that there's no x function, it's just y, g of y times by 1. So you could say that x function in this question is 1, but it's not really there. It is there, it's equal to 1, but it's just a tad different because we've only got things in terms of y in these types of questions. Now, exponential growth and decay follows these equations. So a good example is modelling diseases, but also populations may be restricted by predators or lack of food. So there are two ways of solving these equations, and we're going to do a number of these questions solving them both ways. Way number one is to regard it, like our last video, as separable first order differential equations and write it as 1 on g of y to y is equal to x. Number two is to take the reciprocal of both sides and instead integrate dx to y is 1 on gy. And we're going to have a go at solving some questions using both methods. So example number one, we're going to divide the ey to the other side, y dash, so 1 on ey y dash is equal to 1. So e to the minus y dy is equal to dx. Integrate both sides, we get minus e to the minus y is equal to x plus c. Take the negative over to the other side, e to the minus y is equal to minus x plus c. Again, we don't need to make that c negative because it's just a random constant. To solve this, we need to take the natural logarithm of both sides. So minus y is equal to ln of c minus x, and move the negative to the other side, we get minus ln of c minus x. They should be curves brackets because I'm not integrating that. Using the other approach though, we can realise that y dash is dy dx is equal to e to the y. And flip it, dx to y is equal to 1 on e to the y, which is e to the minus y. We then can say dx is equal to e to the minus y to y, and integrate both sides. X is equal to minus e to the minus y plus c. We then rearrange for e to the minus y and get c minus x. Take the natural logarithm of both sides and move the negative over, and we get the same answer. So we can solve these questions and arrive at the same answer using two different ways. I personally prefer way number one. So these two next examples will help us model exponential growth and decay. So example number two, we're going to solve using both approaches, y dash is equal to ky. So way number one is to divide the y over and say 1 on y dash is equal to k, which means 1 on y to y is equal to k to x. Integrate both sides, we get ln of y is equal to kx plus c. Notice when we integrate and arrive with a natural logarithm, we make it an absolute value. So then to find the solution, we're going to take the e of both sides, raise both sides to the e, kx plus c. Then we're going to go quickly, let a equal e to the c, which means therefore y is equal to a e to the x. Using the second method though, I've got enough room down here, we're solving y dash is equal to ky. Let's check. Yep, ky. We're going to realise that this is dy dx. Flip it upside down, we get dx to y. 1 on ky. Integrate both sides, we've got x is equal to 1 on k ln of y plus c. Now we're going to times everything over. xk is equal to ln of y plus kc, times everything by k, which means ln of y is equal to xk minus kc, which means y is equal to e to the xk minus kc, And we're just going to quickly go let a equal e to the minus kc. So therefore, y is equal to k e to the x. We might actually, to correct that, we might, k e to the a e to the kx. I think I actually missed out. Yeah, I missed out on a k up here. You might be wondering, how can I just randomly make a equal to that when we let a equal something else in the previous question? Well, realistically, to do this, so we've got this and this are different, the value of k is just going to end up being -1, so it doesn't actually affect anything. Okay, example number 3. Solve the differential equation y dash is equal to -3y, given the initial value y2 is equal to 50. I personally prefer the second method, so I'm going to solve 1 on y dash is equal to -3, which means 1 on y dy is equal to -3 dx. And if we integrate that, we're going to get ln of y is equal to -3x plus c for some constant c. Take the e of both sides, y is equal to e to the -3x plus c, and I'm going to let a equal to e to the c, so therefore y is equal to a e to the -3x. Alright, now we're finding a particular solution where y of 2 is equal to 50. So 50 is equal to a e to the -3 times 2, which is -6, which means dividing that over, it's 50 on e to the -6, which of course is 50 to the power of 6, or 50e to the power of 6. So therefore the solution is y is equal to 50 e to the 6 multiplied by e to the -3x. Since they're both base e, we can combine this and say 50e to the 6 minus 3x, and that is our particular solution. Okay. First order separable autonomous differential equations. So a differential equation that does not involve a variable of x is an autonomous differential equation. So really this video could be called first order autonomous differential equations. So what I mean by that is that in our logistics equation, it's g of y times by 1, not times by f of x. So we would call that an autonomous differential equation. What we mean by that is that the variable is autonomous of x. Now if x represents time, which it often does, what is happening to this is independent of time. And that's because that our laws of physics, population, radioactive decay, cooling of a kettle, things like that are true for all times. The time doesn't affect, really affect how these things are changing. Yes, they're changing over time, but time itself is not affecting it. So laws of physics are usually independent of time because they always apply. So most general laws of physics hold in all places, provided we factor gravitational forces into our things. So we think of Newton's second law, F is equal to mx double dot, which is F equals ma, and we're going to use that idea a lot in extension 2. So logistics equations help us model lots of things such as exponential growth and decay. So the logistics equation can have a very general definition, and that's y dash is equal to kyp minus y, for p and k being some real number but not 0. So for those of you who do extension 2, we'll be very familiar with partial fractions decomposition, and we can't actually integrate 1 on 1 minus y, but we can integrate 1 on y plus 1 on 1 minus y. And the idea of going from the product of two things on the denominator to the sum of two different fractions is called partial fractions decomposition. So to show that, we're just going to do cross multiplication. So 1 on y plus 1 on 1 minus y, we cross multiply, and that will give us 1 minus y plus y on y multiplied by 1 minus y. And our y's will cancel, so we get 1 on y, 1 minus y. So we've shown that. Part B, we've got to hence solve the differential equation. y dash equals y1 minus y. Now, very importantly with this, we can't expand and then integrate that, because the y dash is implying we're integrating with respect to x on the right hand side, because it's dy on dx, and then we put the dx up to here. So we can't differentiate y with respect to x, so we can't integrate y with respect to x. So the only way we can solve this is by putting everything involving y onto the other side. So 1 over y1 minus y is equal to, times by y dash, is equal to 1. But we've just shown in the previous question that this is 1 on y plus 1 on 1 minus y, and that's equal to 1. Now we can integrate both sides. The integral of both of those, it's ln of y plus ln of 1 minus y, and that's equal to x plus c. Now, you might think, okay, I'm going to take the e of both sides and I'm going to get y plus 1 minus y equals e to the x plus c. But we can't do that, because we can only take the e of both sides when it's a single logarithm on the left-hand side. But we might want to realise that when we plus two different logarithms together, that's the same as timesing, and when we minus, that's the same as dividing. Now, there should actually be a little negative here that I missed. That's because the differentiation of this is minus 1, which means for it to be in this form, we need a minus 1 on the top and then a minus 1 down here. So when we minus logarithms, that's the same as dividing. So ln of y on 1 minus y is equal to x plus c. Now we can take the e of both sides, so y on 1 minus y is equal to e to the x times a. We might say let a equal e to the c. And we have to have a go at making y the subject of this. So y is equal to, if we multiply the denominator up, we get a e to the x minus y a e to the x. Let's add a e to the x to the other side and factorise. We get a e to the x, y plus 1. No, sorry. We want to factorise a e to the x. So we want to factorise y, sorry. So y a e to the x plus 1 equals a e to the x. And we divide by a e to the x and get y is equal to a e to the x on a e to the x plus 1. Now, I personally would leave that as my answer, but you can keep going. The textbook likes to divide everything by a e to the x on a e to the x. And if we do that, we're going to have y is equal to a e to the x on a e to the x, which is 1, over a e to the x divided a to the x is 1 again, plus 1 on a e to the x. Now we might let a e to the x, or just a equal b, sorry, 1 on a equal b. And 1 on e to the minus x is 1 on e to the x is e to the minus x. So this is 1 over 1 plus b e to the minus x. And that's another way of doing that. Okay, the next thing we're going to have a look at is using differential equations to find the second derivative. So sometimes if we want to find the second derivative, it can be tricky to differentiate because the function itself might be quite hard to differentiate. So it may be easier to differentiate the differential equation to investigate the second derivative. So in example 24, we were examining the solution curves to y dash equals y1 minus y. And we're going to prove that y dash dash is equal to y1 minus y1 minus 2y. So let's have a go. We've got y dash is equal to y1 minus y. Let's expand that, y minus y squared. And we want to differentiate this. So y dash dash, importantly, y dash dash is a function with respect to x. So we're trying to differentiate this with respect to x, which is that idea of implicit differentiation. So if we differentiate y, we get 1, but we have to times it by dy dx. Differentiate y squared, you get 2y times dy dx. Now dy dx means y dash. So y dash minus 2y y dash. Take out y dash, we get y dash 1 minus 2y, which is what we wanted to prove initially, but we've got to prove this second bit. And we do know that y dash is equal to y 1 minus y, so let's replace it with that y 1 minus y, 1 minus 2y. And we're done, we've proven that. Okay, that's the idea of the logistics equation. Thank you.